Hello everyone and welcome to your lesson of physics. In this one, I'm solving some of the structured questions from the topic of vectors. So here we have the first one. The first part reads, distinguish between vector quantities and scalar quantities. So vector quantities are the quantities that have magnitude as well as direction, and scalar quantities have magnitude only. You can phrase it right in the description, but these 2 points have to be there. State whether each of the following is a vector or scalar. Temperature is scalar, acceleration is a vector, electrical resistance is also a scalar. Then we have the this question, the more important one, the question that involves the vector triangle. The weight of the wood is 25 Newton and is held stationary on a slope by means of a string as shown in figure 1.1. Where do we have the diagram over here? So this is a weight, this is a tension in the string, and this is the resultant force. This is the normal reaction force. The normal reaction force is perpendicular to the plane, perpendicular to the thing on which you place the object. It is perpendicular to the surface. You extend the weight vector upward. However, we extend the vector weight, instead of downward, we extend the same vector upward, and we say this vector has the same magnitude. Okay, let me draw it of the same as per the same length, and we state here this vector is having the same magnitude, 25 Newton. Now if this is your vector, this can be called as one of the component of your vector 25 Newton, and the t can also be called as one of the component of this vector. So with this vector you are also getting two components, one from here and one from here. How much would this one would this be? It would be 25 times cos 35 because it is directly with the angle, and the other one would be 25 times sine 35 because it's not directly with the angle. So you get the same answer either way. So it's totally your choice. There are plenty of ways you can solve the question of vector. We can do some of the we can extend some of the lines here for the better understanding. So this is a vector. The tension can be extended in the same direction backward as well. This is the same vector, and we need to find the value of that vector. And I can also extend this line down over here like this. All right, and then this angle would also be 35, vertically opposite angles. This angle would also be 35. So this is opposite to the direction t, and this one is opposite to the direction r. Okay, and we say that we have drawn the same vector but with the opposite direction. So magnitude wise it would just be the same. And matter of fact, we need to find the value of tension. So we're dealing with the magnitude. So even if you change the direction from one way to the other, you change it by 180 degrees, the magnitude would not be affected. So we need to find the vector tension, this one. So you see, if you consider this portion over here, this portion, just take a look at this the portion that I have enclosed. So this is your vector 25, and this thing can be one of the component of this vector. Mathematically, how much? It would be 25 times cos 35 because it is touching the angle directly. And this can also be a component of the vector 25, another perpendicular component, and mathematically it would be 25 times sine 35 because it is not touching the angle directly. So t in this case, because we're not supposed to find the value of r, rather we're supposed to find the value of t, so you can solve it on the calculator. 25 times sine 35. So t equals to, in terms of magnitude, t equals to 25 times sine 35. Then you hit it on the calculator. (25 sine 35). We get 14.3. Into SF we can write 14. So for this one we get 14.3 as the right answer for this one. Yeah. So this is by the method of calculation. And you see, whenever you're dealing with the magnitudes, I repeat, in this question you are not asked about the direction. So if you need to find the magnitude, you can extend the vector forward or backward, and we assume that this vector has the same magnitude. So magnitude wise, it won't make any difference. Alright, or let's check out another way. Another way would have been, let me show you another way. Matter of fact, this is another method which is a scale drawing. Alright, which is a scale drawing. So for this one, you have to establish a scale first. Alright, you need to establish a scale first and then you proceed. So for example, from this diagram, either by scale drawing on figure 1.1, what you can do is you can measure how long this vector is. 25 Newton. So Newton, you can convert it to centimeters to form a scale. So you can see this vector 25 Newton, how much is that? It is, let's say, in terms of centimeter, it is 5 centimeters. So you draw the first vector, one vector over here, like this. Then you draw the next vector according to the same scale, and then you draw the third vector according to the same scale. So this is a method of scale, but for this one, I mean, it is very easy if you solve it mathematically instead of the method of scale. Alright, so here we have the next question. In this one, you're given with two vectors. One of the vectors that we can see here is the wind, and the other one is the velocity of the aircraft or speed in a certain direction. So draw an arrow to show 1.1 to show the direction of the resultant vector of the velocity of the aircraft. So you need to draw the resultant vector on the same diagram to show the resultant velocity. So let me just zoom it out. Alright, so this is the diagram that we have. How many vectors you can see right now? You can see two vectors. You can call the first one, the bigger one, you can call the first vector, but it's your choice. And the second one you can call the second vector. So are these vectors connected and consistent with the head to tail rule? No, they are not, because the head to tail rule says if you have the first pencil over here, let's say the first one, and then you need to connect the second one. So you don't connect the two tips together, rather you place the second pencil at the end of the first one. So it should be connected with something like this. So what you have to do is draw the second vector in front of, at the end of the first one. So instead of vector of wind over there, you draw the same magnitude vector, the same length vector over here. And if I extend it over here on this side, then you know this angle would be 45, and then angle on the inside would also be 45. With the difference of 90, it would be same. So the second vector you have now drawn at the correct position. Now, how do we show the resultant vector? We show the resultant vector from the start point. This is your start point towards the end point. So we join the start point to the endpoint, and you should be joining the tails exactly at a single point, something like this. And then you can represent the resultant vector with two arrows. Just a convention, is totally your choice. If you want to draw with a single line, it's totally okay. So this is your resultant vector. Now let me write down, so we're done with the first part. The next part is determine the magnitude of the resultant vector of the aircraft for the velocity of the aircraft. So you need to find the magnitude of the blue vector, because the blue one is a resultant vector. So what do we do is, there are two different ways you can solve this question. One of them is mathematically, because this side is how much the speed of the aircraft is 250. The other one is, the red one is 36. So I'm going to remove this one from here. This is 36 meter per second. And you need to find the last one. You can call it A, or you can call it X. And then you can use the law of cosine. Whenever you're given with two sides and one angle, you can use the law of cosine. So this one says a square, the missing side, equals to this square of the sum of the square of the opposite sides first. So 250 square plus 36 square minus 2 b c cos a. A is the angle between the two given sides. Then you hit it on the calculator and you can find the value of A. Make sure that you're not forgetting to take the square root, or matter of fact, you can write everything in the square root and write it down on the calculator as it is. Cos 45. So we got 225.9 in 1SF. In 2SF, I'm going to write it as 226. In 3SF, sorry. In 3SF, we can round it off to 226 meter per second. So this is the magnitude of the resultant vector, 226 meter per second. Now, like I said, the same question can be done in a different way as well. You can use the scale drawing to answer this question. I'll do it at the end. So this is by formula. We solved it using the formula, and I'm going to solve it by the vector drawing as well. So for the vector drawing method, you need to first draw a scale, and the scale has to be derived from the diagram itself, because in the question it was given that the diagram is drawn on scale. Okay, there was a bit of couple of sentences at the top of the question which right now are skipped, but in the question it is given that the diagram is drawn on scale. So that means whatever the length you measure of a certain vector corresponds to the actual length. So let's do it by scale drawing method. So for the scale drawing method, first you need to establish the scale. Let me just place it over there. Okay, so I'm going to draw the scale here. So you give the heading scale. It's always recommended that you write like this, scale, and you're converting the vector meter per second into a certain length. So what you do is you find out the vector 250 meter per second, this one. How many centimeter does this vector correspond to? And if you use your ruler to measure the length of this vector, it would be 11.9 centimeters. Okay, either you can draw your scale using this vector or the other one. You can use any of these two. So I suggest the students use a bigger one, that factor, because the smaller one, the chances of error, the chances of uncertainty increases. So use the bigger vector, the chances of you committing a mistake would decrease. So 250 meter per second corresponds to 11.9 centimeters. Then we need to find the length of the resultant vector, and if we know how many centimeters this resultant vector is, we can reverse the scale and we can find how many meter per second would this be. So if you use ruler to find the length of this one, using ruler, the length of this one would come out to be 10.9 centimeter. Okay, because I did it on the paper as well, and the length was 10.9 centimeter. And sometimes the length would vary as well. I mean, when we print it on the sheet of paper, the dimensions are slightly changed. So the image might be compressed or it might be magnified. So depending on the process, the dimension might be changed. So the resultant vector is 10.9 centimeters. And how many meter per second would that be? We don't know. Then you can cross multiply. So what do we have is 11.9 times x equals 250 times 10.9. So 10.9 times 250, and we divide the answer by 11.9. We get 228.9, 229 meter per second. So let me write down this answer as well. From the scale drawing method, we get the answer 229, both with the unit of meter per second. Now, how many significant figures should we leave the answer with? Well, it totally depends on the lowest number of significant figures that you had in the raw data. For example, this one 250, it might be 3SF or 2SF, but the lowest number of significant figures is 2. 36 has 2 significant figures. Okay, so the thing is, with the trailing zeros, these can be significant or they cannot be. They may or may not be significant. So we're not sure about this one, but we can say that the least number of significant figures would be from this data, which is 36. So it can't be, the final answer cannot be with more number of significant figures than 2. So if you round off the first one in 2 significant figures, it would be 230. If you round off the second one in 2SF, it would be 230. So we write 230 meter per second as a final answer.